We got into units last time and also sort of measurements. So remember, there's kind of two types of units that we talked about. One is sort of the English units or the US units that we use here. And there's also, again, the metric sort of system. And sort of a combination of that is the SI system, which is basically made up of our sort of metric sort of system here. And that's oftentimes what we use in chemistry. We talked about last time taking measurements and the uncertainty with measurements. So whenever you take a measurement, there's always some degree of uncertainty with that measurement. The amount of sort of uncertainty it does basically depend on the piece of equipment that you're using. So when we talked about it last time, when we do take a measurement, we do want to always sort of look at two sort of markings that you typically find on a piece of equipment. And those two markings are usually the large marking and the small markings. Now, usually the large markings are the ones that actually do have numbers associated with them. The small markings a lot of times don't have numbers associated with them. The smaller markings are the ones that are really between the bigger markings that do have sort of values written on them. So as we saw last time, maybe here. If we had some type of ruler here, and again, if we were going to sort of measure something, the first thing we want to look at again is those larger markings. And it really is, you can take any two large markings that have numbers, and you really just take the difference between them, and it'll tell you basically what each large marking represents. Obviously, as we saw last time, in this case, we have 2 and 1. So each large marking in this ruler here is 1 centimeter. You then want to calculate or count up really how many of those small markings you have that's between those two. And remember that as we talked about when we're sort of counting the smaller markings, you do want to make sure that you do count them correctly. So we usually always start counting after the previous last large marking. So in this case, we would start counting here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we typically, again, stop at the next large marking. So when you're counting kind of those smaller markings, always start past the last one, last large marking, and then you stop at the next large marking. And since there's 10 of them, again, we could just simply divide this by 10, the larger markings. And that will tell us that each of these here is going to be 0.1 of a centimeter. So again, as we saw last time, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then 2. And once we sort of determine those two things, we're really ready to make any type of measurement that we need to on this device. There are always going to be numbers, as we talked about, that everybody should agree upon. So we can see our little arrow here is about here. And that is at least on the 1.5 marking. So that is what we would record. And again, these are sometimes referred to when you take a measurement as all the certain numbers. And because it's obviously not exactly or 1.6, here's where that sort of estimation or uncertainty comes into play or measurement. And you could or it is. And again, if you think like, hey, I think it's of those two markings, record something like 5. Not always has to be a 5, be like a 7 or 1. And that is what our first uncertain number is. And obviously you would include the units. And this, when you take a measurement, as we talked about, we always want to record all the certain measurements, numbers, and the first uncertain number. And that really is what kind of makes up significant figures. So basically, this guy would have 3 significant figures, again with the glass sort of 5 there. And basically, what you're saying is, I think it's 1.55 centimeters, but it could be, 1.56, could be 1.54, is where the uncertainty lies. As we also talked about at the very end last time, you do want to always sort of look at your equipment because obviously, even though it may have the same number of markings, again, they may represent something different. So if we had, and these were milliliters, and again, if we were reading some type of volume with our meniscus, as we talked about, um, here we would look at our large markings, and in this particular case, we got a 10 and a 20. So the difference when you subtract that is 10 milliliters is what each large marking represents. When we count up again our smaller markings, starting on the one after the large marking. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We again have 10 markings on this particular scale. So again, if we divide that by 10, each of our small markings here is going to represent 1 milliliter. So that would be 11, 12, 13, 14, 15, 16, 17. I think I skipped one there. 18, 12, 13. That's the one I skipped right there. 14, 15, 16, 17, 18, and 19. All right. So in this particular case, if we were looking at our meniscus, which would be right around here, 11, 12, 13, and 14. So it's between 13 and 14. So in this case, 13 would be what we'd want to record. And at that particular case, we do want to record that as all of our certain numbers. And it's not exactly there. It's pretty scribbled in there, but we'll just say, hey, maybe it was a little bit more than half there. We'll go with that as our first uncertain number. And once again here, that would be our significant figures, and this would have 3 significant figures with our uncertain number being that 6 there at the end. So you always want to make sure you take the reading the proper number of digits based on. And again, in this particular case, we did have the same sort of markings, but they did represent different sort of values and stuff like that. So questions on that? Thank you. All right, so let's take a look at a couple more sort of examples. So in this particular case, if we had this as a graduated cylinder here, and yeah, let's just say we have something in that area. All right, so on this particular case here, if we look at our large markings in this particular case represents 20 and 10. So once again, if we take the difference between that, that is 10 milliliters. Now, when we count up our sort of small markings in this particular case, we got 1, 2, 3, 4, and 5 small markings. That means that in this particular case, each of our smaller markings represent how much? There's only 5 of them. 10 divided by 5 is 2, so 2 milliliters in this case, right? So in this case, each of our smaller markings represents 2. That would be 12, 13. 12, I could do it by 2. 12, 14, 16, 18. There we go. In this particular case. And now when we sort of take our reading here of our volume, we are now between the 14 marking and the 16 marking. And the number that comes between 14 and 16 is is 15 that comes between those, right? So in this particular case, the best you could do on this scale is actually 15 milliliters. That would mean, by the way, if that is my measurement, how many significant figures would that have? That would have two significant figures in this case. And which number would be the uncertain number? It would be the 5, yeah. So the 5 here is our estimated digit or our uncertain. So in this case, best you could do is actually a whole number, and that's because when you look at the sort of scale here between 16 and 14, and you're somewhere like in here, there is no way for you to know, for example, where 14 ends and where like 15 starts. So there's not enough room in there for you to figure out sort of the difference between where kind of 14 and 15 starts. So in this case, the best we could do on this particular scale is actually just take it to the whole number. Any questions on that there? So it's really important to make sure you look at the scale so you understand it. Now, when we do give measurements, and when you do give measurements or take measurements here, especially in the laboratory in general at this school, they also would like you to include what is sometimes referred to as the tolerance of the measurement or the uncertainty in the measurement. And you could do that simply by, if we go back here, by taking the smallest markings and basically divide it by 2. So if I take the smallest markings here, which is 0.1 of a centimeter, and I divide it by 2, that will give me what is sometimes referred to or written as plus or minus 0.05 centimeters. Now, this plus or minus 0.05 centimeters actually tells you, for example, how far you should take that reading to. It tells us it should go to 2 decimal places. Actually, at this particular school here, I took in the lab. That's what they and I have to include that here. And so take a measurement like this, write it 5 centimeters plus or minus 0.05 centimeters. I include that instructor within the measurement. So the way that you get that again is simply taking the smallest marking. It's also really helpful because maybe you're not sure how far you should take the reading to, but if you are confident in what the smallest markings represent, pretty much all you got to do is divide it by 2, and it'll tell you basically how far you should take the reading to. However far it goes is how far you should do it. So for example, if we take a look at our other one here, our smallest markings here is 1 milliliter. So if we divide that by 2, that will give us a plus or minus 0.5 milliliters. That is 1 decimal place. That's exactly where we took our reading to. And again, if we were going to write this as a measurement, 13.6 milliliters plus or minus 0.5 milliliters is how we should record that. So it's a really helpful thing. Again, like I said, if you maybe aren't confident in how far you should take the reading, but you are confident when you kind of figure out the small markings, all you have to do is basically divide it by, and it will tell you basically how far to take the reading to. Even works for a weird one like this. Here, our small markings were 2 milliliters. So if I divide 2 by 2, I end up with 1 milliliter, which is a whole number. And that's exactly where we took our reading to. So we would record this as 15 milliliters plus or minus 1 milliliter as well. So again, that's a really helpful sort of thing. In addition, here they do usually want you to include that as you're taking, for example, in labs and stuff like that. But just in general, if you're ever not sure really how far you should take the reading, all you have to do is just divide that small marking by how far you should take the reading to. So, any questions on that or how to get to that plus or minus part? Yeah. Now, let's just say we took our ruler that we saw earlier. And let's say we're going to measure here. And we'll go with like right on that nose there. So if we were going to take a measurement of this guy, and for example here again, we do have our large markings like we had on the previous ruler as 1 centimeter. We once again have our 10 markings in between, 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. So again, we have 10 small markings, which means each of those small markings is going to be 1 centimeter. So when I go to record this, I record 1.4 centimeters, 1.40 centimeters, 1.4000 centimeters. Does it matter which one I record? It does matter. So let's just take a look at each and see maybe what we should record. So let's just take a look at our measurements as sort of proper measurements. If I were to look at this particular measurement, it would have how many significant figures? It would have 2 significant figures. The uncertain number here would be, which one's the estimated or uncertain number? It is the 4. So when you take that measurement, what you're basically saying is, I kind of think it's 1.4 centimeters, but maybe it's 1.5, maybe it's 1.3. So you're basically saying when you take a look at this scale here that, you're like somewhere in that ballpark. That is a lot of error, right? And you could obviously do a lot better on this particular scale based on what it is. So we would not want to do that, because if we did that, we just made our measurement a lot worse than it actually should be. When we take a look at this measurement here, it has how many significant figures? 1.40 it would be 3 significant figures. The uncertain digit in this case would be, it would be the 0 here. So in this particular case, what we're saying is, I think it's 1.40 centimeters, but maybe it's like 1.41 or maybe it's 1.39. Now we're talking about like in there, right, is sort of where our difference is. And based on our scale here, we can see that is pretty much realistic based on what we can do with this particular one. And we do need to record it with that extra 0 in there. Because if we take the 0 out, like on the left there, we really made our measurement a lot crappier than it should be based on the scale that we have, and we made it a worse measurement. Now, on the other hand, if I were to record like this, how many significant figures would this guy have? Guy would have 5. And you're basically saying that the uncertain digit would actually be this very last 0, which there's no way on this particular scale that far out, right? So it's not good to add extra zeros, many extra zeros. So I have too little. You don't want to have too many. You want just the right amount in this particular case. So that does require in certain cases for you to add a 0 in there, perhaps, to maintain the proper number scale. And you take that measurement. By the way, this one as well, we would divide that by 2 and get our plus or minus 0.05 centimeters. And we would record 1.40 centimeters plus or minus 0.05 centimeters. Again, just by doing that, if you're not sure, it will again tell you you should take this reading to 2 decimal places. And that would hopefully tell you got to add probably a 0 to it as well. Any questions on any of those there? So it's really important to take a look at the scale. Also, obviously, really important here, you do take that reading to the proper number digit. Take a look at it. Sure, talk. And we record all those uncertain numbers plus the first certain numbers plus the first uncertain numbers. That does represent our significant figure. With the uncertainty basically lying within the last significant figure. So this may not make sense right now, but um, the uncertain or the estimated digit is in the last significant figure. It may not always be the last number that's written. So, but it should always be the last significant figure. And precision. When we are looking at accuracy, how all precision or talk about a set of numbers basically are one another. So pretty much got the right answer. Precision is how many times you could do the same thing over and over and get the same answer. Maybe you're right, maybe you're wrong. Ability of a lot of times with accuracy, we look at something known as percent error, calculate something like percent error. A lot of times when we look at precision, we do something like standard deviation or deviation. And we're going to throw some darts at it. Goal here is obviously sensor. So I throw my three darts like here or over here. My accurate size. Now I am probably should have thrown darts at that case, right? Pick up my pride and my dart here, and I give it a go here and go to double or nothing. So I throw my darts here. I go boom, boom, boom. Now my accuracy. But like it's not accurate, right? You could be really wrong. So I be things wrong the same way every time you get them. So start. All right, so now I throw my darts. Precise. Yeah, and that's the goal, right? If you're doing an experiment or something like that, you do want to be accurate. You do want to kind of get the right answer if there is obviously a right answer. And you want to be able to be very precise and be repeatable and do the experiment multiple times. That's why in a lot of times when you do experiments, you do multiple trials to see if you could get the same results every time and you can repeat the experiment. You do want kind of the right answer as well. So that's sort of what we talked about there. So again, on the left there, we can see we are not accurate or precise. On the right, we are very precise, but not so accurate. And there in the middle where we hit the bullseye, we are accurate and precise. All right, so let's take some readings here off of the scale, and I'm not sure if it moved or not, so I'm not sure if the right answers are right or wrong down there. I don't think they're right. So I think some scaling moves, so we won't load with those. Take an actual again, we want to look at our large markings, which do have numbers, and again, here we have a 2 and a 3. So the difference, you subtract that, is a 1 centimeter difference between them. Once again, we also want to count up our small markings, again, starting after the last large marking and ending at the next large marking. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, if we divide that by 10, our small markings in this case is going to be 0.1 centimeters. So this would be basically 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8 right there. So it is at least 2.8. So we do want to record that. Again, we do need to kind of take a look at it and see where it's at. It's not exactly on the 2.8, it's just past it. And once again, in this case, you may look at it and obviously not think it's halfway there. So again, maybe think just a little bit further. So maybe record a 2 in our centimeters. This can again being our certain numbers. This is our first uncertain number. And obviously, we do want to include our tolerance. So if we divide that by 2, that gives us plus or minus 0.05 centimeters. That is 2 decimal places. That is where we took our reading to. So plus or minus 0.05 centimeters in this particular case. Any questions on that one there? Okay. All right, same deal here. I think it again probably moved a little. So let's just take a reading where it ended up. And once again, big numbers to the lines there. All right, so again on this one, we do have our large markings similar to the last one. We have a 9 and an 8, so the difference there is going to be 1 centimeter. We also have our same 10 markings between the two, which means again our small ones should be 0.1 of a centimeter as we divide that by 10. And once again, even before we begin, since I know this for sure, I can divide that by 2 and know right off the bat I do need to take my reading to 2 decimal places in this particular case. So that would mean that this would be 8.5 in this case. That would be 8.6, 8.7, 8.8. So it does look like we were at least 8.7 in this case. And again, that's going to be my certain numbers. And in this case, maybe you feel like it is kind of between the two markings there. So maybe you'll record a 5 for your centimeters. Again, that being our uncertain number, along with our plus or minus 0.05 centimeters in this particular case. Any question on measurement there? So as I mentioned before, they do want you here at the school to kind of include that plus or minus when you do take. You do not need to um, well, that will come out, but it's use the number by itself. All right. So as we talked about again, it does depend on sort of the piece of equipment that you're looking at. So if we take a look at this sort of graduated cylinder here, and in this case, we are going to read from and the U-shaped meniscus we talked about. You do always want to read from the bottom of the meniscus. And again, if you take a look at our large markings here, we have a 30 and we have a 40. So if we subtract those two, that's going to give me 10 milliliters in this case. If we count up our sort of markings, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings happening between that. Divide that by 10, that means my small markings in this case is going to be 1 milliliter. And that would mean something like this is like 31, 32, 33, 34, and so forth, all the way up there. And once again, small marking, you don't want to have to worry about not taking the measurement to the right number of digits. All you got to do is divide that by 2. That's going to give you your plus or minus, in this case, 0.5 milliliters. So even before I take the measurement, I automatically know that my measurement is 1 decimal place, and that's where I should end up. Here, we'll take a look at it. And big line here, 35, 6, 37. That means 6 in this case. Once again, you're going to try to find where that is. Maybe you feel like it is halfway there. We would record a 5 milliliters plus or minus 0.5 milliliters as our reading in this particular. So on that one there. And again, you can see they felt when they zoomed in that it was a little bit more than half. So they went with 36.8, which is again why that is sort of the uncertain number, right? I looked at it, I looked like it was halfway. Some that another very common chemistry burette, and we'll use it this semester, and you'll definitely use it pretty much. Maybe not organic too much, but burette's a little bit of a different piece of equipment, and that is because when you have a burette, you do fill it from the top, and it does sort of empty from the bottom. And when you look at the scaling on a typical burette, it actually increases as you go down. So when you start at the very top, it's actually 0, and then it goes to 1, 2, 3, all the way down. And it's sort of the volume increases as you kind of go down. And that means that if you were, for example, somewhere in this region here, because it empties from the bottom and you fill it from the top, you're actually 1 point something, not 2 point something. So it's really important to make sure you take the reading properly. You start at 0, and then it kind of empties out from 0. So wherever it's at is where you want to read it. And again, if you're kind of between two numbers, you're usually the top number above 1 point, whatever it may be, is sort of where you're at. 2 point something here. Also, again, if we take a look, you could kind of see here, we would do the same thing. You could also see, as I mentioned, it is increasing as we go down. That's 28, 29, 30. So the volume's getting larger as you go down. We would do our same thing. Our large markings, once again, as they show there, is 28 and 29. So that's going to be a 1 milliliter in terms of our large markings. Our small markings, once again, if we count up our dashes here, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, we have 10 small markings, which means in this case, each of the smaller markings is going to be 0.1 of a milliliter in this particular case. So again, at this point, if you're very close to 0.1 for your small marking, now you can just divide this by 2, and that will get you your plus or minus 0.05 milliliters. Now you don't have to guess, you know, just from doing that, I need to take my reading. And if we take a look here, our meniscus, I don't know, somewhere. That would be right around here, 28.5. That'd be 28.6, 28.7, 28.8. So again, so we got 28.5, 28.6, 28.7, 28.8, and 28.9. So we are definitely between the 28.8 and the 28.9. We would record a 28.8. And once again, here we do want to take a guesstimation and maybe record a 5 in this case, and your milliliters, all your certain numbers, one certain number. And again, going to 2 decimal places. So something like 28.85 mil plus or minus 0.05. Okay. Your SGUs. Most of the time, excuse me, most of the time, 2 decimal places is usually kind of how far you usually take it, but you always want to look at the scaling. Questions on that one? We'll talk more about it when we do use the burette, but another very common error that people make is, as I mentioned, and if this was, say, a 50 milliliter burette, a lot of times when people fill it to the 0 mark, they have a bad habit of recording, for example, 50 milliliters because they filled it all the way to the top. It's 50 milliliters. So they're at 0 and they record 50. And you never want to do that when you are using something like a burette. You always want to record the actual number it says on the scale. Because what you do when you use a piece of equipment like this is you take an initial reading, and then you take a final reading when you're done, and you subtract the two, and that tells you how much you added. So if you recorded the top number, which should be 0, as 50, and then the next number as 20, you're going to be way off of sort of what you actually added. So, because you only added really 20 milliliters, right? You didn't add 30 milliliters. So it's really important, especially with a burette, that you always record the actual number it says. Like that. Any questions on that one there? Hey, they even got the same answer as me. That's good. All right. All right, so why don't you take a look at this one here? Why don't you take the proper reading, see what you come up with, along with the plus or minus that should go with it. Again, this is another burette, it looks like. Okay, let's take a look. So once again, just looking at our large markings. It doesn't really matter which ones you look at, but just want to find two large markings. And in this particular case, again, we have a 30 and a 20. So if I subtract that, that is going to give me 10 milliliters. Taking a look, and I'll just go above here so I don't mess up too much the other markings. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. So we do have 10 markings. So our small markings in this case is going to actually be 1 milliliter, right? 10 divided by 10 is 1 milliliter. At this point, if I know for sure it's 1 milliliter, I'm just going to take that small marking divided by 2, and that's going to tell me plus or minus 0.5 milliliters. So once again, before I even take my reading, I know my reading should end up with 1 decimal place and have the proper reading. So if we take a look here, looks like here would be 21, and basically right on it, looks like in this case. So we would record this 2 milliliters. The problem is I cannot just record 22 milliliters in this case because based on this scale, as I could figure it out right here, I could actually go to 1 decimal place. So because it's right on the nose here, this is a case where I do need to put the 0 in to maintain the proper number of significant figures. Because if I just recorded 22, I would have only 2 significant figures, right? When I should actually be having 3 in this case, right? So again, I would make my measurement a lot worse. Case. Again, in this talked about, you do need to actually add. It looks like it would be D actually on this one. Actually, the right answer is there. It's good. So any questions on taking measurements? Obviously, we're going to do a lab today of nothing but taking all this stuff. So earlier, and that I also mentioned it included in calculations, though. Okay. All right. So now that we understand sort of where significant figures come from, let's talk about what is considered a significant figures and sort of the rules for counting significant figures and sort of how we get there. So first off, when we count significant figures, we basically always start left to right on the number. And we really don't start counting significant figures until we hit the very first non-zero. So you're really not going to be counting significant figures till you look at a number, you go left to right, and you hit the very first 0 number. And that's because all non-zero numbers are significant figures. So obviously, as you can see here, starting left to right, that's our very first non-zero. Everybody else is a non-zero. So this guy would have 4 significant figures. Now, when we talk about zeros, that is something that sometimes confuses people. And there's really 3 types of zeros that we come across. The first type of zeros was sometimes referred to as a leading zero. Those are basically all the zeros that come before you hit the very first non-zero number. So all the zeros before that first non-zero number, those are not going to be significant. So when I look at that number there of 0.0049 going left to right, I'm not going to start counting here until I hit the 4. That means that all these zeros here are not significant, and the 4 would be significant, and the 9 would be significant. And that is how we get to 2 significant figures in this particular case. So again, left to right, hit the first non-zero, start counting your significant figures at that point. If I take a look at 5.004, starting here, that is significant. These zeros are what are referred to as captive zeros or trapped zeros. They basically are zeros that are between two non-zero numbers, and zeros that are between two non-zero numbers are going to be significant. So that would be one significant figure there. These two are trapped, so that's 3, and one more makes 4 significant figures. So if you have some zeros between some non-zero numbers, they will be considered significant. Zeros to come before your first non-zero number are not significant. And that leaves us the last type of zero, which is pretty much the one that confuses a lot of people, and that is the trailing zero. So these are the zeros that come at the end. And the reason it sort of confuses people sometimes is in certain cases, these zeros at the end will be significant. And in other cases, the zeros at the end will not be significant. What determines whether or not the zero at the end is significant is there a decimal point actually written anywhere in the number? So if there is a decimal point actually written, not a decimal point like we did with like scientific notation where you're like, I think it's at the end, even though it's not written. It does need to be actually written in the number. If it's written anywhere in the number, it will be significant. So if you have a decimal point, it will be significant, the zeros at the end. So if I have 600 written like so, this is going to have how many significant figures? It is going to only have one significant figure, which is this. Again, there is no decimal point written in this number, and that would be the only significant figure. By the way, the uncertain number in that case would be which number? It would not be the 0 because it's not a significant 0, right? It would actually would be the 6 in this case. So this is what I was talking about earlier. People always get in the habit when they're asked like that question, like, oh, it's always like the number that's at the end. It is not always the number at the end. A lot of times it is, but it is always the last significant figure. So because the 6 here is the only significant, so when you take a measurement like this, if this is like a measurement, you're basically saying is I think 600, but hey, maybe it's like 500, maybe it's like 700. That is really your uncertainty. That's a lot of uncertainty there. As I have one significant figure, and it's a crappy number of significant figures, right? It's not the greatest measurement there because there's a lot of error within that, right? If I did 600 with a decimal there, how many would it have now? It would have now. And which one would be the uncertain digit in this case? It would be the last 0 here, right? And what we're saying in this case is, I think it's 600, but maybe it's like 599, maybe it's like 601, a lot less error, right? Because now, all right, the very much better measurement. So once again, it does need to be actually written the decimal point. So if I have a number like 0.0003004230, and those are going to be meters. I have no idea how you make that measurement, but maybe. How many significant figures does this number have? All right, let's take a look because I don't know. It's just writing numbers. So let's just see here. So starting left to right, are any of the they are not, right? Because I have not hit the first non-zero. So really, I'm not counting until I hit the 3 in this case. So that's my very first sort of significant figure. Now I got a couple of zeros that are trap zeros. So those guys are good, right? Those are going to be significant. We have a non-zero significant, non-zero significant, non-zero significant. Now we have the 2 zeros at the end. Are they significant? The answer is they are significant because even though the decimal point's not near them, there is a decimal point way over here, and that's going to make those zeros significant as well. And what was that, 8, I think? 4, 6, 8 significant figures here in this case. So sometimes people think that the decimal point's got to be like near those zeros or anything like that, and they don't. It just needs to be anywhere in the number to make those zeros at the end significant. That's also why sometimes people will think that these zeros are significant because they come after the decimal point, but they're not significant because, again, in this case, we're not counting until we get to here, right? So they're outside that first non-zero number. So even they're not counted because we haven't really started counting our significant figures yet. Any questions on that? Also, a reminder that we talked about scientific notation earlier. And remember that when you write a number in scientific notation, all the numbers that come before the times 10 part are significant. So in this case, this would be 2 significant figures in this particular case. And remember that when you have a number that's written in scientific notation, you should look at the significant figures sort of before you convert it into a decimal or something like that, how it's written in scientific notation. Lastly, as I also talked about, sometimes the only way, for example, to give a correct answer may be to write it in scientific notation. Like if I had 12,000 and I wanted 3 significant figures, the only way I could do that is to write it in scientific notation. There's no way for me to write 12,000 in decimal form and still have 3 significant figures. Any questions on that there? All right. Now, when we talk about significant figures, those usually involve measurements, and measurements have some type of uncertainty associated with it. Another type of number that we come across is what's known as an exact number. And an exact number is pretty much achieved 1 of 2 ways. You can either count it, or it's like a definition, an exact sort of definition. So for example, if I have like 3 pens on my desk or something like that, I'm not going to do any type of experiment to figure out how many pens I got sitting up here. I'm just going to simply go 1, 2, 3, or how many pens I got up on my desk, and I'm going to count it. Classic textbook example is a bucket of apples, and you're just going to count how many apples you have. The definition part are like these. There are certain definitions. These are what are really referred to as equalities. Equalities are 2 things that represent the same amount of something, but are on different units. So if I had 100 pennies and $1, that represents the same amount of money. They're just on different units, right? So you have to. These are some exact equalities and definitions. 1 inch is 2.54 centimeters exactly. 1 pound, 453.6. They use that as an exact measurement here. 1 foot is 12 inches, 3 feet in a yard, and 1.609 kilometers in 1 mile. So once again, no this here. When we look at sort of an equality or definition, if you remember, there really was 2 types of units that we talked about, the US units and the metric units. So typically speaking, if you're using an equality, which as we'll talk about later on in this chapter, basically means you're going to be using like a conversion factor, and it came from an equality that's a US to US conversion, like 12 inches equals 1 foot, you could consider that an exact measurement. If you're using some type of metric to metric sort of conversion, like 100 centimeters equals 1 meter, you could also consider that usually an exact number. You don't have to worry about it. The only time you really have to worry about sort of a definition or equality like this, in most cases, is if you cross over and use like a metric and a US sort of conversion. That usually means you do have to look at the significant figures when you do a calculation. Now, why is exact numbers even sort of talked about? It's really talked about because of this. Exact numbers, technically speaking, could have as many significant figures as you want. basically, because they're exact number. Because of that, we technically, when we do calculations, and we're going to talk about doing calculations and giving answers to the proper number of significant figures, when we do calculations that involve exact numbers, we don't even have to worry about the sig figs that there are in those numbers or in those sort of conversions. So if I was doing something with 1 foot is 12 inches, I don't have to worry about the significant figures and that sort of calculation part. We could just sort of ignore them. The only time, again, is like I said, if you cross over metric to English, you do actually have to look at the conversion and take that into account when you're doing significant figures. And we'll talk more about that a little bit later on when we get into sort of conversions as well. Any questions on that there? All right, so obviously here that has 3 significant figures. Once again here, not going to start counting until we get to here. And the 3, the 0, and the 4 here are going to be significant. This guy would have how many significant figures this has? This is a number that's written in scientific notation, which means all 4 of those are going to be significant. So again, if you have a number that's written in scientific notation, all the digits there will be significant. You got 3 significant figures here as we're starting left to right. And here we are going to start left to right. That's significant. The 0 here is not going to be significant, again, because there is no decimal point actually written in the number in this particular case. And lastly here, not going to start counting until I hit the 9. At this point, I could count. Significant, trap 0, significant, 2 significant. This 0 is going to be significant, again, because there is a decimal point in the number. So starting at the 9, all of those guys there are going to be significant, and we would have 4 significant figures in this particular case. Yes. It would not in this case because it does technically, it is technically a measurement in this case because it's 125 grams. So again, with any measurement, there's going to be uncertainty and significant figures. So, yeah. So technically for our purposes here, and in most cases when they talk about exact numbers, it does have to be, in most cases, the way you'll come across it is probably like a definition, like 12 inches is 1 foot. Or for example, if you said like, you're doing a calculation, you had like 1 atom of something, right? 1 would be probably considered an exact number because it'd be just something like you technically would count and stuff like that. So it's got to be something like that. Typically, if it's like a number that's really derived from a measurement, that's really where we have uncertainty and significant figures associated with it. Other questions? All right. So let's talk a little about rounding. We do follow normal rounding rules here. So if you are going to round, you look to the right of the number you want to round to. And if the number to the right is 4 or less, we typically just drop the number. If it is kind of 5 and above, we typically will round the number we want to round to up by 1. So we do want to do simple rounding. So we also want to be careful with rounding in 2 situations. So typically speaking, if you are doing a calculation that involves multiple steps, so maybe you did a 1 step, you got an answer, and now you're going to take that answer and do another calculation with it. You're going to get an answer, you're going to go take that number and now do another calculation with it. So multiple calculations in a row, typically speaking, we really don't want to round a lot until you get to the very end of your calculation. You should definitely keep track of everything, but you really should not round too much until you get to the very end. Because if you round a lot after each individual answer, you're just going to move yourself away from the correct answer. You're kind of moving yourself further and further away from the correct answer. So you can do 1 of 2 things. Most people will keep what is sometimes referred to as guard digits, a couple of extra digits if you need to write the number down past where technically you should round to. And that usually will help any type of sort of rounding errors that you have just simply by rounding a little bit too much along the way. The other thing that we don't want to do is we don't want to do any kind of crazy sort of rounding. So let's say I have 13,333 and I want 2 significant figures, What is my answer? Is it 13? Is it 13,000? Is it 1.3 times 10 to the fourth? Well, let's take a look at these. I saw some shaking of heads on each of them. So let's start with this one here. 13. How many significant figures does it have? It does have two significant figures, so that's good. Now, the problem with 13 is, although it does have two significant figures, it doesn't really mean the same thing as we started with, right? So if I owed you $13,333 and said, hey, I'm just going to pay you two significant figures, here's $13. I don't think you're going to be very happy with me, right? Maybe you would. I don't know. You look like friendly people. But we definitely changed the meaning of the numbers. So even though we got the right number of significant figures, wanted that around. Very common error you make, very focused on getting the right thing. Although it is correct. Step two, because I did not write a decimal. And 13,000 and 13,000, much the same meaning. I get a 333 teacher discount or something like that, right? So, and maybe you take the 13,000, much better than 13. So we would want to write it like that, right? Because we have the right number of significant figures. And once again, we did not really change it like this. The answer is yeah. And times 10 to the 4, right? So 1, 2, 3, 4. Scientific notation. Here was the example 12,000, written like this. First off, how many significant figures? What is the number here? It is the 2, right? So if I wanted, like I said, 3 significant figures in this case, I could not write 120 because it does not have 3 significant. The point, it now has 3 significant figures, but once again, does not mean the same thing, right? 120 and 12,000, that's a big difference. So I would, the only way I could do this, I can't just put a 0 point there at the end, right? Because now I have 5 significant figures. I can't just put the point after there and keep the zeros because now it still means $120, right? Or 120. It doesn't mean 12,000. Still has now 5 significant figures. So if you wanted 3 significant figures, I'm sorry, I want 3 on that one. If we wanted 3 significant figures, the only way I could do that is scientific notation in this case, right? 1, 2, 3, 4. Now I have something that has 3 significant figures. The value associated with it. So there is sometimes very, not all the time, but it does pop up. Again, the significant figures, you got to kind of write it in scientific notation because you can sort of control how many significant figures you have when you do that. Any questions on the rounding? So try not to do any extreme rounding or anything like that. So if we take a look here on our rounding, if we wanted 2 significant figures, that's going to take me to the 5 in this case. I'm going to look at the 7, and the 7 is greater than 5. So I'm going to round up, and I will end up with 36. Here it is the 8. I'm sorry, the 8 here. We're going to look at the 2. The 2 here is less than 4. Technically speaking, I would drop this. Drop all the, keep the meaning. We also want to make sure we don't. Look at here, second thing is here we will just drop the zeros at the end and end up with 0.0026. Why did I not add zeros in this case? How many significant figures would it have if I put the zeros there? It would have 4, right? And that's not what we were shooting for. So again, some cases you want to drop to 0. Some cases you want to. And obviously here, if we go to the 2, we're going to look at the 8. We're going to round up. Gets us a 1.3. Any questions on that there? All right, so now that we understand hopefully significant figures, how to count significant figures, let's talk about how we do significant figures in calculations. And basically, there's two kind of groups of calculations that we typically do, and that is we multiply and divide, or we add and subtract. And if we multiply and divide, the answer we end up with is the same number of significant figures as the number with the least number of significant figures. So we're looking at sig figs when we multiply and divide. We're always looking at the smallest or the least number of significant figures. So if I took a 4.25 and I times it by a 1.2, I am multiplying here. So I'm looking at significant figures. That is 3 significant figures. That is 2 significant figures. So my answer should end up with 2 significant figures in this case. And in this particular case here, if we did that, 4.25 times 1.2, we will end up with 5.1, which is 2 significant figures, it looks like. So that's good. That's ridiculous. Now, if we add or subtract, also the smallest decimal place on number of decimal places. So if I took 1.25 and I added it to 3.6 and I added it to 4.111 and I did a little addition here, it looks like a 1, a 6, a 9, a 7, 8. I get 8.961. This case, because adding or subtracting, again, we're looking at decimal places, not significant figures. And if I look at decimal places here, that is 2 decimal places, 1 decimal place, 3 decimal places. That means technically we go 1 decimal place in this case. And I look to the right and I see a 6, which means I should round up. My 9 is going to become a 0, and then my 8 is going to become a 9. And I actually should end up in this case with 9.0. Yeah. In this particular case. That makes it important if you were then just going to do another calculation. Fine. Stop any questions on that. Now, if you're doing some type of combination like 1.5 point, but 6, 3, 6, 4. Here we need to kind of keep track. So math operations would tell us that we would do what first is multiplying. So since we're multiplying here, we are going to look at the significant figures. That has 3 significant figures. That has 2 significant figures. That means that technically speaking, when I'm done with the top part, I should end up with 2 significant figures. Now I'm going to take that number and divide it by the bottom, which is dividing, also looking at significant figures. So that would be 2 significant figures divided by 4 significant figures. That means that my answer should end up with done. We did that 1.32 times 4.2. That's going to give me, technically speaking, when I do the top part, 5.544 divided by 6364. Now, as I mentioned before, I would not round this at this 5, but I would keep track of it. So as I mentioned, sometimes people will also sometimes like to put like a little line over, like, hey, that's kind of where this number really should end, and it just kind of keeps you remembering where you should end. And then do the rest. So I would take this whole number and divide it by the bottom, and I will end up on my calculator 0.0008711 on my calculator screen. And again, we're going to go to two significant figures. Remember, these are not significant. One significant figure, two significant figure. Looking at the one to the right, in this case, we are going to just drop it. And we would end up with point. Sometimes you do multiple steps along the way. You try not to round until the end. You do want to kind of keep track of it. Like I said, you don't have to write everything in your calculator. Maybe just keep a couple extra digits. That's usually pretty good, and that usually will keep you in a pretty good place. So if I did 4.25 divided by 0.25, and then I added it to 1.322, what should the answer be? All right. So I'm going to obviously do my division first. And since I'm dividing, I am going to look at significant figures. So technically, this has 3 significant figures. This guy has 2 significant figures. That means technically, when I do my top part here, I should end up with 2 significant figures. And if you do that, 4.25 divided by 0.25, hey, got a lucky sig figs. So technically, I should have 17 at this pace. Now I'm going to take that 17, I'm going to divide it, actually add it here to 1.33. So we'll add it to 1.322 actually. And that'll give me on my calculator 18.322. Now, when I come to add, I do need to switch from significant figures to decimal places in this case. This has 3 decimal places. This has none, right? Smallest number of decimal places is the one with no decimal places. So here we would actually go to a whole number, which would be 18. Here we would not round up or anything like that, and we would end up with 18. Okay. Keep track of it. All these avoid a lot of rounding, keep track of it, clean everything up at the end. Try to take no extreme rounding along the way and keep some extra digits as you're doing the calculations, and that'll avoid a lot of the calculation or rounding errors. Any questions? Calculations with significant figures.